Now we will look at how to do incremental analysis when we have nonlinear two-port elements in a circuit. Okay. Now, with one-port elements, we have seen that we could write the equations, then expand the nonlinearities in a Taylor series around the operating point, neglect higher order terms and so on. But finally, that is not what we do routinely. What we did was, for every nonlinear component, we came up with an equivalent that is valid in the incremental picture. And for a two-terminal nonlinearity, that is a resistor. Okay. A two-terminal nonlinear element like a diode, it is a resistor. What we want to do now is to figure out what is the equivalent of a two-port nonlinearity. Okay. So, in the incremental circuit, we substitute the two-port by this equivalent circuit, which is valid of course only for small signal increments, and go ahead with the analysis. And by definition, whatever equivalent we come up with will be linear, because we will be neglecting all the higher order terms. Okay. This is a two-port nonlinearity, and these are the voltages and currents. Now, we know that I1 and I2 are some functions of V1 and V2. Okay. Now, let us say we choose some operating point. I define the operating point as V1 0, V2 0, and which give rise to currents I1 0 and I2 0. You can think of this in many different ways. You can imagine that you have connected voltage sources V1 0 or V2 0, and these give you currents which are I1 0 and I2 0. But it does not have to be like that. It is basically, you have this nonlinear element in a circuit, and at some particular point where you choose to do the analysis, you have solved the nonlinear equations and found the solution. That combination of voltages and currents happens to be V1 0, V2 0 and I1 0 and I2 0. Essentially, it is the first point at which you do the analysis. Okay. But if it helps you, you can think of it as something like this, and then you can apply increments to these voltages. Now, by definition of this nonlinearity, I1 0 has to be equal to F1 of V1 0 and V2 0. Okay, because these are valid for any voltages and currents. So, it clearly has to be true at the operating point, and I2 0 will be F2 of V1 0 and V2 0. Now, like I said, let us imagine that there are some increments around the operating point. Okay. Again, it is easy if you think of V1 0 being changed to V1 0 plus delta V1, V2 0 being changed to V2 0 plus delta V2, and so on. Okay. You can think of it that way, but it does not have to be like that. It does not have to be voltage sources applied here. Any change in conditions because of whatever reason, you will have a new set of voltages and currents which are V1 0 plus delta V1, or sometimes you use lowercase v1, and V2 0 plus delta V2, and the currents will be I1 0 plus delta I1, and again sometimes you see lowercase I1 used here, and I20 plus delta I2. Okay. So, all it says is that it could be changed from the operating point. And of course, again these voltages and currents have to satisfy these relationships which define the nonlinearity. Okay. So, we have the operating point conditions here, and we will have conditions with the increments. Also okay. Now, the modus operandi is very simple. So far we haven't said anything new, all we did was to express new voltages and currents as the original, the operating point voltages and currents plus some incremental quantities. That by itself is not a significant step. Now, we will expand these relationships in a Taylor series. This will of course be a Taylor series of two variables, and they are very useful by their own right, but for us we do not need to go into too many details. So, all we need to know is that we expand, let us say I will take F1 as an example, the same holds for F2. In a Taylor series around or about the operating point. So, what will we get? This will turn out to be this is the operating point, right. So, let me write it like that. And Taylor series is nothing but you will have a constant term, you will have first order dependence on the variables and second order dependence on the variables and so on. Okay. Now, we have two variables. So, the first order terms will be these which have partial derivatives with respect to each variable, that is partial derivative of this function with respect to V1 times delta V1, and this partial derivative has to be evaluated at the operating point, because the derivative itself changes depending on the voltages and currents. And you will also have the partial derivative with respect to V2 also evaluated at the operating point times delta V2, and these are linear or first order terms. Okay. These are linear in terms of the variable, which is the incremental voltage delta V1 or the incremental voltage delta V2. And then you will have higher order terms, we will not have to worry about them. You will have terms which are proportional to delta V1 square and something with delta V2 square, and also something with delta V1, delta V2 and so on. Okay. So, all of these are basically higher order terms. Okay. Now, of course, we will not have to worry about them, because what do we do with these? We just neglect them. Okay. We assume that you can always find a small enough value of delta V1 that these are even smaller, because the idea is the following: if delta V1 is very small, okay, compared to something, delta V1 square is even smaller. Okay. Now, it is harder to see with dimension variables, but you can think of a dimensionless quantity, right. As I make let us say a quantity x go from 1 to 0, x square will also go from 1 to 0, but much more rapidly. Okay. Because when x is half, x square is only 0.25, when x is 1/10, x square is already 1/100th and so on. Okay. And x cube will go down even more rapidly and so on, that is all. So, you can always put some limit on the size of delta V1 and delta V2, so that these higher order terms are negligible. Okay. And that is the only way to define the limits for this incremental small signal analysis. Okay. That depends very much on the nonlinearity and the operating point you choose and so on. I say neglected, what I really mean is delta V1 and delta V2 are small enough so that these can be neglected. Now, what do I do after neglecting them? I recognize that this I10 is nothing but F1 of V10 V20, because that comes from here. Okay. So, that part cancels from the two sides, and as before, as with the one port element, I have a relationship between the incremental quantities delta I1, delta V1 and delta V2. And what kind of relationship do I have? That is between delta I1 and delta V1 and delta V2, it is a linear combination. Delta I1 is nothing but a linear combination of delta V1 and delta V2. Okay. And exactly the same thing happens for delta I2. I do not have to repeat that. It is exact same expressions, except that instead of F1 over here, you will have F2. You have to partially differentiate F2 with respect to V1 and with respect to V2 and find the values of the partial derivatives at the operating points. So, the relationship between the incremental variables of a nonlinear two port is the following. So, delta I1 will be partial derivative of F1 with respect to V1 at the operating point times delta V1, partial derivative of F1 with respect to V2 at the operating point times delta V2, and similarly this is the partial derivative of F2 with respect to V1 at the operating point, and okay. So, delta I1 is a linear combination of delta V1 and delta V2. Delta I2 is also a linear combination of delta V1 and delta V2. Now, we chose V1 and V2 to be independent variables while expressing the nonlinearities. It does not have to be like that. I1 and I2 can be independent variables, or it can be a mixture I1 and V2 or V1 and I2. Then these partial derivatives will have different dimensions. That is all that is there to it. But for our purposes, we will keep this form. Even if there is a different representation of the nonlinearity, you should be able to easily calculate the small signal representation. Okay. Now, of course, I am sure all of you are familiar with this set of equations. Okay. What is this? After all, this whole thing is a linear two port with voltages delta V1 and delta V2 and port currents delta I1 and delta I2. And when you talk about linear two ports, these would have been expressed as Y11 delta V1, Y12 delta V2, and delta I2 is Y21 delta V1 plus Y22 times delta V2. Okay. So, when you have voltages as independent variables and currents as dependent variables, the set of parameters that relate them, it is known as Y parameters. Sometimes you express them in matrix form as well, and the notation is Y11, Y12, Y21 and Y22, where the first number denotes the effect, that is delta I1, and the second one denotes the cause. Okay. So, Y12 relates the effect of delta V2 on delta I1. Okay. And clearly you can see the correspondence between these Y parameters and these partial derivatives. Okay. So, Y11 clearly is partial derivative of F1 with respect to V1 at the operating point, and similarly Y12 is partial derivative of F1 with respect to V2, and similarly for these two as well. Okay. So, what we get finally is a linear two port network. In case of a two terminal element or a one port element, we got a resistor. Now we have a linear two port network, and the circuit equivalent is also the same as what we used for a linear two port network. Okay. Now these parameters are known as small signal Y parameters, for obvious reasons, because these tell you the linear relationship between small signal increments. It is only for increments that are sufficiently small that the linear relationship holds. Okay. So, what we do is the following: when we encounter a nonlinear two port in a circuit, first we obtain the operating point by the usual painful way of solving any nonlinear equation. Okay. Once we have the operating point, things are easy. All we do is substitute the nonlinear two port with a linear two port, and what are the parameters of the two port? They are nothing but partial derivatives of the large signal characteristic at the operating point.